Imagine you are standing on a launch pad watching a rocket rise from the surface of a distant world. Tremendous energy is released, fire, force, acceleration. Yet even this machine at full power is bound by a universal limit. Uh, no matter how advanced our engines become, no amount of fuel, no clever engineering can push an object through space faster than light itself. This limit is not technological, it is geometric. It is written into the structure of space-time, taught. More than 100 years ago, Albert Einstein showed us why. Space and time are not separate things, they are woven together into a single fabric, and motion through this fabric reshapes how time flows and how distances are measured. As speed increases, time slows, distances contract, and at the speed of light, the equations themselves reach a boundary. What if the limit of light speed is not a barrier of energy, but a boundary of geometry? Physicists have debated this for over a century. How would you answer it? Today, we ask a dangerous and fascinating question. What if, instead of relying on the brute force of rocket propulsion to exceed the speed of light, we consider whether modifying the space-time metric itself can enable effective superluminal faster than light travel? In this video, we will build, step by step, a mathematical framework that allows an observer to transition from subluminal motion through the light barrier and into a superluminal frame without breaking the laws of relativity. For centuries, physics was built upon the ideas of Isaac Newton. Space was a fixed stage. Time flowed the same everywhere, and motion happened within this unchanging arena. In this view, the universe was absolute, rigid, and universal for all observers. But experiments at high speed revealed something strange. Light refused to behave like ordinary motion. Its speed remained the same for all observers, no matter how fast they moved. This simple fact shattered the Newtonian picture. Einstein resolved this mystery by uniting space and time into a single entity, space-time. In this new picture, time does not tick at the same rate for all observers, and distances are not universally fixed. Motion through space-time reshapes both. Einstein's ideas were given precise mathematical form by Hermann Minkowski, who described space-time using a geometric metric. This metric measures space-time intervals. It is a rule that tells us how to combine time and space together, not just distances in space. It is this geometry, not the spacecraft's engines, that ultimately enforces the speed of light. If you lived in Einstein's time, would you have believed space-time could bend, or would it have sounded impossible? To understand motion in space-time, we must first agree on how we describe events. In physics, an event is not just a place, it is a place and a moment in time. We collect these four pieces of information into a single object called a coordinate vector. Here, c is the speed of light, ensuring that time, t, is measured in the same units as space. The position of an event is located at our spatial coordinates x, y, and z. Together, they define where and when an event occurs in space-time. Now let us describe motion. For simplicity, we focus on motion along a single direction. The z-axis, the forward velocity of an object moving this way, is written as, this tells us something profound. The object moves through time at speed c and at a velocity v, through space only, along the z direction. Even when standing still in space, we are always moving through time. To mathematically allow an observer to cross the light barrier, we introduce a function f of v. which scales time and space along the motion direction. This function determines how space-time stretches or compresses as velocity increases. Think of it as a dial that controls the flow of time and space along your motion. F of v behaves differently depending on speed. We can divide it into three regimes. When velocity, v, is less than the speed of light, f of v is equal to 1, and we get the traditional transformation for observers. When the velocity is approximately equal to the speed of light, we get a gradient or slope in the geometry that allows us to cross the light barrier. Here, beta equals v over c, and f of c is the critical value that controls the transition near the speed of light. When velocity, v, is greater than speed of light, f of v is equal to -1, and we get a set of equations that describe tachyon motion. Think of f of v as a dimmer switch or gate controlling spacetime. At low speeds, the dial is off. Near the light barrier, Fc stretches time and space along the motion axis. Beyond light speed, the dial flips, opening a superluminal path. An analogy helps. It's like driving up a hill. Subluminal speeds are the flat road. Fc is the steep hill peak, where everything slows and stretches, and superluminal speeds are the downhill acceleration aided by space-time itself. F of v is the mathematical control that lets an observer transition smoothly through these regimes, making the impossible journey beyond the speed of light mathematically consistent. Next, we introduce the concept of a tetrad, or Vierbein. Think of it as a set of local rulers and clocks that move with the observer. These rulers measure distances and time locally, stretching or compressing as the observer moves. By choosing a non-trivial tetrad, we are redefining local rulers and clocks. When that tetrad is used to construct the metric, it encodes curvature or engineered geometry, effectively changing the space-time structure experienced by the observer. Mathematically, the tetrad is written as a simple matrix which scales space-time differently along time and motion directions. Notice how the motion direction, which here is along the z-axis, gets multiplied by the square root of f of v, while perpendicular directions remain unchanged. Imagine walking on a treadmill. The belt moves forward beneath your feet, accelerating you in that direction, but the sides remain stationary. In the same way, f of v sets the speed of space-time along the motion axis. The tetrad applies this scaling locally to the observer, stretching or compressing time and distance. With this tetrad in place, we can transform the familiar Minkowski metric into a new metric that depends on speed. It's the first step toward shaping space-time so that the observer can mathematically cross the light barrier. By carefully controlling f of v through the tetrad, we can imagine stretching the fabric of space-time along the motion direction while leaving perpendicular directions unchanged, much like guiding a ship along a corridor of malleable space. Now we apply the tetrad to the familiar Minkowski metric, which describes flat space-time. The transformation stretches time in the motion direction according to f of v. Mathematically, this is written as where the Minkowski metric is multiplied by the matrices of two tetrads, giving us a new modified metric. Notice that only the time component and the motion direction along z are scaled by f of v. The other spatial directions remain unchanged, maintaining stability perpendicular to motion. This selective scaling is what allows the observer to cross the light barrier mathematically without violating the local speed of light. The metric along the direction of motion stretches or compresses, forming a corridor in which the observer can travel faster than light. All the heavy math here is a precise description of this wave-like corridor, and it is the core principle behind the idea of a warp bubble. In simpler terms, the observer is carried along by the deformation of space-time itself. Time and distance along the motion direction adjust according to f of v, while the perpendicular directions remain unaffected. This is the first step in understanding how faster than light travel could be possible, not by breaking physics, but by carefully shaping space-time. The line element is a fundamental tool in relativity. It tells us how to measure space-time intervals between events, using the metric we just transformed. Here, the scaling function f of v directly affects the time and distance along the motion direction. Below the speed of light, space-time behaves normally. Time flows, distances are measured in the usual way. As we approach the light barrier, time slows along the motion direction, and distances stretch. The observer feels no unusual force. Everything is measured locally with their tetrad. Beyond the light barrier, the metric flips. Time and space along the motion axis reverse their roles, effectively opening a corridor through space-time. This is the mathematical foundation for superluminal travel, a warp bubble or wormhole, where the observer is carried faster than light without locally breaking physics. Imagine standing on a conveyor belt. As you reach a certain point, the belt speeds up beneath you. You move faster than your surroundings, yet you feel no extreme forces. Similarly, the line element tells space-time how to carry an observer across the light barrier, stretching time and distance along the motion direction, while leaving perpendicular directions unchanged. F of v is the dial controlling this conveyor belt of space-time. F of v controls the gradient of the light barrier. Smooth gradients spread the stretching over distance, reducing energy spikes. Sharp gradients act quickly, but require more energy. In this way, F of v determines the shape and safety of the superluminal path. Think of the warp bubble as a river carrying a boat faster than the water around it. F of v adjusts the current strength along the riverbed. Our understanding of space and time has a rich history. Newton imagined absolute space and time, a fixed stage upon which the universe played out. This view held for centuries until Einstein revealed that space and time are connected, flexible, and affected by motion and gravity. Einstein's relativity showed that massive objects bend space-time itself, curving the paths of light and matter. Hermann Minkowski later formalized this idea into four-dimensional space-time geometry. The Minkowski metric gave physicists a precise language to measure intervals in this flexible, interconnected fabric. Fast forward to modern physics, where we confront the ultimate speed limit, the light barrier. Miguel Alcubierre proposed a warp drive metric that allows a bubble of space-time to move faster than light, carrying an observer along without locally breaking physics. This is where functions like f of v come into play, mathematically shaping space-time for superluminal travel. In essence, the story of faster-than-light travel is the story of human curiosity and mathematical imagination. From Newton's absolute stage to Einstein's flexible space-time, from Minkowski's precise metrics to Alcubierre's warp bubbles, each milestone shows how physicists extend our understanding of the universe. Today, Researchers explore modifications to the Minkowski metric as a tool to probe superluminal paths. These models let us ask fundamental questions. How would space-time stretch? What energy would it require? And what limits does the universe impose? While still theoretical, these ideas form the blueprint for imagining journeys beyond the light barrier. Let's take a step back and summarize what we've learned. First, in the subluminal regime, when the observer's speed is less than the speed of light, v is less than c, f of v is approximately 1. Space-time behaves normally. Time flows and distances are measured as we expect, just like in everyday life. Next, in the luminal regime, as the observer approaches light speed, v approximately equals c. F of v approaches the critical value fc. Time along the z-axis slows and distances stretch. It's as if space-time itself is bending to accommodate the ultimate speed limit. Finally, in the superluminal regime, when v is greater than c, f of v becomes negative. The metric along the motion axis flips, mathematically opening a warp path through space-time. This is the core principle behind theoretical faster-than-light travel. The observer is carried along a corridor of space-time without locally breaking physics. In summary, the combination of tetrads, the transform metric, and f of v gives us a complete framework for transitioning safely through subluminal, luminal, and superluminal regimes. Subluminal speeds are the normal universe. Luminal speeds stretch time and space along the motion direction, and superluminal speeds open a corridor for potential warp travel. This framework allows physicists to explore faster-than-light motion in a mathematically consistent way. We've journeyed from Newton's absolute space to Einstein's relativity, explored Minkowski's space-time, and even peeked into the mathematical corridors of faster-than-light travel. This is just the beginning of imagining what warp travel could mean for physics and exploration. If this exploration sparked your imagination, please like and subscribe for more. Next, we'll dive into the energy, stability, and engineering challenges of superluminal travel, taking these mathematical ideas one step closer to reality.